Lesson 4.5, addition and subtraction formulas. Talking about compound angles, we start with a definition of what a compound angle is. A compound angle is a trigonometric expression, we're in the world of trig, that depends on two or more angles. So if you take the cosine or sine of an angle, this time that angle can be built from two or more angles, and there are a handful of formulas that go with it. We could draw a diagram and use our distance formula to derive those addition and subtraction formulas, but we're not going to do that. I'm just going to give them to you, and then we'll go on to apply them in our examples. So the first one is the addition formula for cosine. The addition formula for cosine takes the cosine of angle A plus B. So this is any old angle, but it can be broken up into two smaller angles which are added together. This is equal to the cosine of A times the cosine of B minus the sine of A times the sine of B. So when would we ever want to do this? Well, if we have an angle here that we don't know very much about, but we know we can break it up into two special angles, and then we can break it up into special angle A and special angle B, then we know the value, the exact value of cosine of A and cosine of B, and we can multiply them together. And we know the exact value of the sine of A and the sine of B if we're talking about A and B are special angles. And then we can just do arithmetic to get an exact value of this, even if we didn't know anything about the original angle. We also have a subtraction formula for cosine. Cosine of A minus B. So let's say you can break up an angle and call it A minus B, where A and B are special angles. It's helpful. And that reduces to cosine of A times the cosine of B plus the sine of A times the sine of B. So how to memorize that one? The addition formula for cosine has a subtraction in it, cos, cos minus sine, sine. And the subtraction formula for cosine has cos, cos plus sine, sine. We also have an addition formula for sine. So the sine of A plus B is equal to the sine of A times the cosine of B plus the cosine of A times the sine of B. So you'll be using these regularly. You'll get used to it and you'll actually probably memorize them. But the sine law, the sine rule here, the addition or formula, the addition formula for sine has sine times cos, where you have A and B, and then you're adding it to cos times cos and sine, A and B. Okay, you could do that a couple different ways. Okay, and a subtraction formula for sine. Sine of A minus B equals the sine of A times the cosine of B minus the cosine of A times the sine of B. Okay, so the sine formula for addition has addition in the middle. The subtraction formula for sine has subtraction in the middle. And this time, instead of being paired with your own ratio, you're with the opposite ratio. So sine A cos B, and then sine B cos A. You could say it that way if you wanted to remember it that way. That's fair too. Multiplication is commutative. Let's roll down to tangent. Leave yourself a little gap because this is going to have a numerator and a denominator over here. So the addition formula for tangent is, in the numerator, tan A plus tan B. In the denominator, 1 minus tan A tan B. So 1 minus the product of the tangent of A and the tangent of B. And the subtraction formula for tangent is, in the numerator, tan A minus tan B over 1 plus tan A, tan B. And again, we could spend time deriving that using a diagram and some angles and the distance formula, but we're not going to. We're just going to use it. You can also find these written on the back of your magical trigonometric formulas sheet. Okay, this unit and next unit, you're going to spend a lot of time proving trig identities and other trig statements. So we're going to get used to doing it the right way. And in example 1, you're asked to prove the addition formula for cosine given the subtraction formula for cosine. So we have the addition. We're supposed to prove the addition. So we're going to go, this marker is failing me. We're going to go with our left side, right side strategy. On the left side, we have the cosine of a plus b. And on the right side, we have the rest of the addition formula, which is cos A cos B minus sine A sine B. And the example is saying that we are allowed to use the subtraction formula of cosine. Okay, so what are we going to do? Well, if we can express this angle addition, this compound angle, as A plus B, then we can express it also as A minus negative B. And now all of a sudden we have a subtraction formula for cosine where one of the angles is A and one of the angles is negative B. So part of being able to prove trig identities is being able to kind of solve it like a logic puzzle, find ways of making it look how you know it's allowed to look without cheating. And in this case, we knew we could use the subtraction formula, so I have to be able to see that addition is really just subtracting a negative, or subtracting a negative is really just addition. So from here, I can apply the subtraction formula for cosine with A and negative B being my two angles. So we end up with the cosine of A times the cosine of negative B plus the sine of A times the sine of negative B. Okay, but if cosine, or if... Now we can use some of the other things we already know about sine and cosine and the properties and identities of them. So we'll take down our cos of A, but the cosine of negative B, the cosine of the negative of an angle, is the same as the cosine of that angle, right? Because, and you can think about that as cosine being the distance along the x-axis of any point. So if I take the angle negative b and I take the angle positive b, well, I'm at the same distance along the x-axis, okay? So the cosine of negative b is the same as the cosine of positive b. Well, let's look across at our other term here. Sine of A can't be reduced any further, but the sine of negative b is equal to negative the sine of positive b. Let's look at what happens when we simplify that. And remember, whenever you're proving something, you're kind of looking back and forth from left side to right side, seeing, am I getting closer? Yes, we have the whole first term, cos A cos B. And actually, if I take sine A times sine B and I have one negative factor, then I have the second part as well, minus sine A sine B, and that is equal to the right side. Okay, so take what they give you, use what you know, use other trig identities and formulas in your proof, and go from there. Okay, example 2 says, prove the addition formula for sine using correlated angle formula and subtraction formula for cosine. So let's first write down left side, right side of what we're trying to do. We take the sine of A plus B. And on the right side, we'll take the other part of this compound angle formula for the addition formula for sine, which is sine of A cos of B plus cos of A sine B. So here's where we're starting. Here's where we're trying to get, okay? Well, again, we're allowed to use the subtraction formula. So we're going to use the same strategy with this compound angle. We can rewrite that as the sine of A minus negative B. And now we can use, yes. So we're taking our addition formula for sine on the left side and the other part of it on the right side, which is sine A cos B plus cos A sine B. And we are allowed to use our correlated angle formulas. So the correlated angle, the correlated ratio with sine is cosine, right? Sine and cosine. And how do they relate to each other? This was on your quiz. I can rewrite the sine of A plus B as the cosine of, and we're going to use a square bracket here, but this is pi over 2 minus A plus B. So if you remember your correlated, don't write this, but just a quick review. If you have the sine of 12 degrees, that's equal to the cosine of 90 minus 12 degrees. Okay? Or, for instance, if we're dealing in the world of radians, if you had the sine of, I don't know, pi over 3, that would be equal to the cosine of pi over 2 minus pi over 3, where pi over 2 is equal to 90 degrees. Okay? These are then correlated ratios, and these are the correlated angles. Okay? Pi over 3 is correlated to this angle. So all we did is express this sine compound angle in terms of cosine by using the correlated angle formula. Okay? So that's how we get to that. Now what we need to do is rearrange this a little bit. And again, this isn't going to be immediately evident to you, but after you do a bunch of them, you'll see it a bit more clearly. I'm going to distribute that negative sign to both of the terms in the binomial. So we're going to end up with the cosine of pi over 2 minus A minus B. Okay? And then we're actually going to group the first two terms. And now we still have a subtraction formula, a cosine subtraction formula, but we've changed our two angles. Algebraically, we've been able to change the two angles without actually changing the value of the compound angle. Okay, does that make sense? We just algebraically, we distributed that so that we don't need the brackets. And then we said, okay, we're actually going to group these two first, and we're going to now consider pi over 2 minus A as one of the angles and B as the other angle, and we have a subtraction formula. Why would we do that? Well, hopefully this looks familiar to you. This is one of our angles that we can work with and reduce. So anyway, we'll keep going. Right now we're going to apply the subtraction formula for cosine, and it says that you can take the cosine of your first angle, which is pi over 2 minus A, times the cosine of your second angle, which is B, and add the sine of your first angle, which is pi over 2 minus A, times the sine of your second angle, which is B. And again, we can look across and say, okay, I think I'm getting a bit closer. I've got in my first term, I have a cos B here and a cos B here, and I have a sine B here and a sine B here. And now we can go back and use our correlated formula that you see on your magic sheet, where you have the angle pi over 2 minus a. So these are the correlated angles. And we see that the cosine of pi over 2 minus a can actually reduce to the sine of a. So now you have the sine of a cos b, the product of those. And next term, the sine of pi over 2 minus a actually reduces to the cosine of a. And we carry over our other factor of the sine of b, and we look across and we see that does equal the right side. If this part, going from here to here, is the tricky part, then you just need to double check your notes on correlated angles. This is kind of a new application of algebra. It's just the rules of algebra that allow us to do that. So that's just seeing it a couple times and then getting used to being able to do it if you need to prove these things on your own. And then we just did what it asked us to do. We said instead of using it gave us the addition for sine, but it said that we could use the correlated angle for cosine. So then I think, okay, right away I have to express this in terms of this. How do I do that? Well, you use correlated angles. Okay? Okay, example 4 is where you really see that it's two angles being added together, because we're going to actually draw these two angles and then find the addition of them. So we've got some information. We know that the sine of A, and you have a little drawing over here that's going to help us as well. We know that the sine of A is negative 4 over 5. So if I'm over here and I'm going to draw a little triangle that helps me, I know sine, if I'm in my SOHCAHTOA world, sine is opposite over hypotenuse. And I know that the sine of A is going to be negative in a couple of these, but we're going to be down here in quadrant 3, and we're going to have an opposite of 4, negative 4, and a hypotenuse of 5. So in order to make a triangle with my x-axis, how do I know that we're in the third quadrant? It tells us that angle A is in between pi and 3 pi over 2. Okay, so I know that we're in the third quadrant. 1, 2, 3.
Are A and B different angles though?
A and B are different angles, yes. So we're going to make angle A first, and it has an opposite of, and you can really draw this angle anywhere here in this quadrant. I know that it looks a little bit more like, I think like this. Okay, but it doesn't really matter how you draw it, as long as you form a right triangle with the x-axis. And we are told that the opposite is negative 4 and the hypotenuse is 5. How do I know that
Sine is opposite over hypotenuse?
Yeah, and basically if you're in quadrant 3, then coming down, the y value has to be negative, and also the hypotenuse will never be negative. The value of the hypotenuse will never be negative. Okay? It's a diagonal line. Either the horizontal line or the vertical line or both will be negative, but never the hypotenuse. But from this triangle, I can now find out the length of my missing side by using Pythagorean theorem. Essentially, I have 5 squared minus negative 4 squared equals my missing side squared. We can just call it x squared for now. But I could also know that I'm in a 3, 4, 5 right angle triangle. Okay, so this ends up being 9. So my missing side length is 3. And I know it's negative 3 because I'm going into quadrant 3. So I'm just going to write that here in order to keep it out of the way. Okay, now this is angle A. We're given another angle. We're given angle B, and we are told that angle B is in between pi over 2 and pi. So angle B is here in quadrant 2. It's in between pi over 2 and pi. What do we know about it? We know the cosine of B is -5 over 13. Well, cosine is adjacent over hypotenuse. So I know that my adjacent side is -5. And again, you don't necessarily need to draw these things proportionately. We're basically just using the same diagram for two triangles, thinking about them kind of separately. And the hypotenuse then is 13, which is probably way up like this. That is really ugly. Okay, if you have your right angle triangles, if you're good with right angle triangles, you know that this is a 5, 12, 13 triangle. If you don't know those things, there's no better time to learn. But otherwise, you can just go into your Pythagorean theorem again. And we can call that missing side length y, and so y squared, so you end up with 169 minus 25, that equals 144, equals y squared, which means y equals 12. It is positive. Okay? So now we have a whole bunch of information that allows us to get our values of certain things when we're applying the addition formula for tan, which is what we're using here. Okay, so we're going to take our tan of A plus B, which equals, from your yellow sheet and from your notes, the tan of A plus the tan of B in the numerator over 1 minus the tan of A, tan of B, the product of those two things. Now you can see how our diagram is fairly helpful and why the formula is helpful. We've taken this A plus B, which we really know nothing about, and we've been able to split it into just the tan of A and just the tan of B and the tan of A times the tan of B. Okay, and we have all of the sides of two right triangles representing angle A and the information for angle B. And so we can actually put in our exact values for the tangent of A. We know the tangent of A is going to be opposite over adjacent from triangle A. Okay, opposite over adjacent is -4 over -3. I'm going to sub those in exactly as they are, and we'll reduce them as we go. So the tangent of A is actually 4 over 3. So in the numerator, I'll leave myself some space here. In the numerator, we have 4 over 3 plus the tangent of B. So we look in triangle B. The tangent is opposite over adjacent. So we have 12 over -5, or -12 over 5. Let's look at the denominator. We have 1, and then we have minus the product of tan A, tan B. Well, we already did the work on that, so we literally just need to copy them down. Tan A is 4 over 3. Tan B was -12 over 5. And now all of a sudden we have an expression with no tans, sines, or cosines at all. And we can just perform our basic algebra on this. We want to, in the numerator, if we're going to add these two fractions, we want to express them both as fractions over 15. So we end up with, and I'll just write every step. So if 4/3 as a fraction over 15 would be 20 over 15 minus 36 over 15. So that's 20 minus 36 over 15. In the denominator, we have 1 minus, And to multiply fractions, we just go top times top, bottom times bottom. So here we have 4 times 12 is 48 over 15, 3 times 5. And the easiest way to do this is going to be express the numerator and denominator as fractions over 15. So I'm going to reduce my numerator. This is negative 16 over 15. Negative 16 over 15. And then the denominator I can also express as a fraction over 15. So I have 15 over 15 right here. 1 is 15 over 15 minus 48 over 15. 15 minus 48. Nope, I made an error. It's plus 48. So we have a negative and a negative. It's going to be plus 48. Quick fix. So we have 15 over 15 plus 48 over 15. So we have 15 plus 48, which is 63 over 15. And then because your numerator and denominator are both expressed over 15, you could multiply top and bottom by 15, and you'd get negative 16 over 63. And you think that's a ridiculous number, but we did it right, so we carry on. That is the tangent of angle A plus B based on the criteria that it gave us for angle A and B. Okay, we drew a diagram, we figured out the missing side in triangle B, figured out the missing side in triangle A using Pythagorean theorem, and then we subbed in our known values for each trig expression here, and then we used arithmetic carefully to simplify and reduce, and we end up with the tangent of A plus B is negative 16 over 63. Okay, one more for now. This one's fairly convoluted. You're not going to like this, not even a little bit. It says prove that the sine of x plus the sine of y is equal to that funny statement on the right. Okay? Let's bring in some tools that we know. We know the addition formula for sine and the subtraction formula for sine. Okay, so we know that the sine of a plus b is equal to the sine of a cos of b plus the cosine of a times the sine of b. And then line up the subtraction formula underneath this. So we also know that the sine of a minus b is equal to sine of a cosine of b minus cosine of a sine of b. What are we going to do with that information? Let's draw a line under it. And let's put a plus sign here. So you can see what's going to happen when we add these things up. Okay? On the left side, we can't combine these expressions really anyway. So on the left side, we end up with two expressions. We end up with sine of a plus b plus the sine of a minus b. And on the right side, we end up with this first expression twice. So 2 times sine A cos B. And what happens to our last two terms? They cancel out. You're adding and subtracting the same value. That's just 0. Okay? From here, we are going to replace A plus B with just the letter X. And we're going to replace A minus B with the letter Y. And then we'll plug them back in later. It's just easier to talk about this as one angle, one entity, and not mess it up. Also, it's because if we look at the problem, we're trying to prove a statement with x plus y, and right now we're working with a's and b's. But if you look at the left side, sine x plus sine y, that's essentially what we're working with right here, except this is x and this is y. Okay, so we are going to let a plus b equal x, and we're going to let a minus b equal y. Now, we're going to apply the same thing. If we add these two things, these two statements, we end up with 2a equals x plus y, because the b's will cancel out. And then to get a, we now have a equals x plus y over 2. Okay? Now that's starting to look a lot like what we have on the right-hand side. We can do the same thing in order to get the b's out of this, but we do it by subtracting. So if we have a plus b equals x and a minus b equals y, just like we have here, and this time instead of adding them up, we're going to subtract them. We end up with a minus a is 0, b minus negative b is 2b, and here we have x minus y, which gives us...
Where do we get a subtract b equals x? Oh no, never mind.
over here. So we basically...
Oh, no, I thought we had a different... I thought it was a subtract b equals x. I can't see it.
It's all
I
good.
was confused.
Okay, so now we really just need to take this and sub it in to what we have. So the sine then of a plus b plus the sine of a minus b becomes, from up here, so we're just taking this again, I'm copying it down again, equals 2 times the sine of a cos of b. But we also now have a new expression for each of these things. We have a new expression for the sine of a plus b, because we said a plus b equals x. And we have a new expression for a minus b. We said a minus b is y. And on the right side, we said that a is equal to x plus y over 2. And the cosine of b, well, we said b is equal to x minus y over 2. So a bit of a logic problem for you there, subbing different things out and in, but you're learning some skills. You can add or subtract 2 true statements to create a third true statement. Okay, that comes from grade 10, equivalent equations. And then eventually you're trying to make that left side look like that right side.